All right. So what do you guys want to talk about? Okay. So let's say, so this would have been test 3 stuff, sections 5.1 and 5.2, but that's all the like rational function stuff. So let's say, for example, we have that function. So, I mean, the thing that makes it a rational function is that you've got polynomials showing up in the top and bottom, right? Rational is like ratios, like fraction. So basically a fraction made of polynomials, right? And stuff that we need to make sure that we can do with this, we need to be able to figure out the domain, of course, any asymptotes, and intercepts. So a couple of, sort of like key things dealing especially with domain and the idea of finding like vertical asymptotes is that because this is a fraction, we need to make sure that we don't divide by 0, right? So finding the domain here, and that ties into finding discontinuities or vertical asymptotes. Basically what we need to figure out is when would the denominator be 0 and then like work around that, right? Sort of avoid those values. So the first thing I'm going to do is deal with that part. Let's take the denominator aside. Set it equal to 0. Because it's already factored, setting that equal to 0 and solving should be like pretty straightforward, right? The 3 doesn't matter. Either x minus 5 is 0 or x plus 2 is 0. So 5 and -2 would be the 2, and it's just those two places that would give you 0 in the denominator of that function. And again, therefore, that makes that function undefined. So since it's those two and only those two values where that happens, the domain for this function is everything else, right? It's defined for all real numbers except for when bad stuff happens. Those are the only two places when bad stuff happens. Does that make sense? Yeah, okay. So the domain then is everything except for those 2 points. How would we write everything except -2 and 5? All real numbers minus those 2 things. So -infinity up to negative. So think about it on a like number line, right? It's everything toss -2 and 5. So -infinity to -2, parentheses for open interval, right? Meaning you can get close to it, but don't include it. Then -2 to 5, then 5 to infinity. Right, that's this piece and this piece and this piece, excluding just those 2 points. And furthermore, there are vertical asymptotes at those 2 points. -2 and 5 both give you, if you look back to the original function, if you think about like plugging -2 in, that's going to give you some number, some non-zero thing divided by 0. So as you approach -2, then obviously you can't divide by 0, but as you approach -2, you get things that are sort of increasingly like ill-behaved, right? You get very big y values back. That causes it to do the asymptote thing and sort of break off and point toward either positive or negative infinity. The same thing happens at 5. If you had, probably not gonna say this, but or this week anyway, but if you had like x minus 5 showing up at top and bottom, where it would like appear to cancel, that's what would give you like a hole in the graph rather than an asymptote. Just yeah. Basically zeros of the denominator that aren't sort of like balanced out. That's where vertical asymptotes happen. Okay, so that's all from looking at where the denominator is 0. Other stuff. Horizontal asymptote. I haven't organized things very well. Can I erase this stuff? Does everybody have what they want there? Okay, cool. All right, so horizontal asymptotes, what are we looking for? Leading coefficients, yeah. Horizontal asymptotes are in behavior. It's what happens eventually. So it's what happens when x is big. So it's the leading terms because the leading term is the one that, sort of like wins eventually, right? So what we do is think about what the leading terms would look like. If I took all the stuff in the top and all the stuff in the bottom and multiplied it all out, we would end up with 2x squared and some lower order terms that I don't care about over 3x squared, and again, some lower order terms that I don't care about, right? You don't have to actually multiply it out. Just think about what it would look like, right? The first part would be x times x, so x squared, and then there's a 2 parked out in front of it, so the leading term would be 2x squared. Similarly, denominator x times x would be x squared times 3, so 3x squared, right? I only need the leading terms, so I only need to worry about the biggest ones. 2x squared over 3x squared would reduce to 2 over 3. That means that eventually, like what we're doing by only looking at the leading terms is saying, okay, when x is 100 bajillion, the square term is so much bigger than all the other terms, than the linear term or the constant part, that they basically don't matter anymore. So when x is 100 bajillion, this is basically in the ratio of 2 to 3. That means the thing is going to level off and there's going to be a horizontal asymptote, and that's where it's going to happen. Y equals 2/3. And again, that's all leading terms, right? Because it's in behavior. So just like for polynomial stuff that I think a lot of people, have like sort of an easier time with in the moment, polynomial stuff, you look at the leading term to determine what's going to happen. Rational stuff, you look at the leading terms because there are 2, top and bottom, but in kind of the same way, that's what the horizontal asymptote's really doing. Okay. Okay. All right, and then intercepts. We got everything we want there. Okay, cool. Intercepts. How do you find an x-intercept? Second. Plug in what? Intercepts are, what do we mean when we say intercept? Where it crosses the coordinate axes, right? So when it hits one of the axes, then one of the things is 0, right? So x-intercept would be where y is 0. y-intercepts would be where x is 0. And that's true for everything, not just here. But if y is 0, and we set this whole thing equal to 0, what do we do to figure that out? Trying to solve this. Where is this thing equal to 0? Don't look at it as a big scary algebra thing. Look at it as a fraction. What does it mean for a fraction to be 0? Can the bottom be 0? No. Because we've already dealt with that, right? Division by 0 is undefined. We already dealt with that in the domain stuff. Bottom can't be 0. You want the whole fraction to be 0. It's got to be the top, right? Or if you want, you can think about it as multiply both sides by the denominator, and it sort of disappears, right? Because on the right, you multiply by 0. But it's got to be because that is 0, which means that x plus 1 is 0, or x minus 3 is 0. So -1 and 3. So our x-intercepts -1 and 3. All right. And then the last thing would be finding the y-intercept. If an x-intercept is where y is 0, everybody have everything? Have that? Okay. I guess you can go back to the, I am recording this, so you can go back later and look at stuff if we go too fast or anything. Y-intercept would be where x is 0. So we just plug 0 in. 0 plus 1, 0 minus 3, 0 minus 5, 0 plus 2, -6 over -30. So 1 over 5. Yes. Oh, sorry, you can't see all that. There you go. Now you can see it, but it's tiny. Okay. So all of that stuff, I give you a rational function. Setting the, it's kind of about like knowing how and where to sort of break the different pieces up and interpret what that tells you, right? So setting the denominator equal to 0 tells us where the thing is undefined, right? So that gives you the domain, or gives you the things that are not in the domain, but gives you what you need to find the domain. That also tells you the vertical asymptotes. Looking at the in behavior or the leading terms on top and bottom, that tells you about horizontal asymptotes. If they are kind of balanced like they are here, 2x squared over 3x squared, the x squared reduce out, you get 2/3. Right? If it's if it were sort of like top heavy or bottom heavy, then you either get no asymptote or an asymptote of 0, depending on which of those. Setting the numerator equal to 0 gives you x-intercepts, because setting the numerator equal to 0 is really setting the whole fraction equal to 0. And then a y-intercept do the same thing you always do, right? Just plug in x equal to 0. Okay, everybody feel all right about that? Okay, cool. So that's, that's not a bunch of like difficult stuff to work through that's like conceptually dense, right? Keeping track of what all the stuff is. But if you have it all down, that's, 20 points or something that are like pretty easy to get because again, there's not a ton of stuff that you have to like work out there, right? It's not like a thing where there are a bunch of places where you can make a mistake or something. If you understand what's going on, then you understand what's going on. Okay, what else? Sure. Are you looking at on the review? Yeah. So this is 27 on the final review. I'm gonna do E. All right, 2 plus 3i divided by 2 plus I. We are to simplify this. What do we need to do? Multiply by almost. Right. So look at the denominator. Change the sign though. 2 plus I to 2 minus I. Change that like middle sign for reasons that are going to become apparent in a minute, and I'll come back to. So we're doing that here, which means we also do it on top and bottom, so that this pink thing I'm multiplying by is really just 1, right? Just a weird representation of 1. But again, we're going to do it because it works. What we're trying to do is get the imaginary part out of the denominator because I don't know what it means to divide by a complex number, right? So we handle division by complex numbers by turning it into something where I don't have to handle division by a complex number. We just move the I out of the divisor. So multiply all that out. Okay, so I get that. Now we're just gonna like simplify, combine like terms and stuff. Let me focus in on the denominator first for a second, just to kind of illustrate again, like why we did what we did. What happens in the denominator when we go to clean stuff up here? The 2 i's cancel out, right? Minus 2i plus 2i, those terms cancel because they're the same but opposite. That's why we did what we did here. That's why we multiplied not by the denominator exactly, but by its conjugate, flipping that sign in the middle, so that this would happen. Because now what I have in the denominator is 4 minus I squared, but I squared is really -1. So really what we have in the denominator there that we're dividing by is 4 minus -1. So I've changed this from a thing where I'm trying to divide by 2 plus I, which again, I don't really know what that means, into a thing where I'm dividing by 5, which just means like, hey, you 5 people, you each get a fifth of this cookie or whatever, right? That's why we do what we do. Okay, and then work the rest of the stuff out on the top. So 4 minus 2i plus 6i, so plus 4i. Then minus 3 times -1. So that's 4 plus 3. And then for complex numbers, like to be, exact or technical about it, we should split it up into the real part and the imaginary part, just kind of separate those. That also helps you see if you can reduce anything. Nothing reduces here, so we just leave that like that. This, though, is the part that you have to kind of like remember, right, to get into the thing. Once you've got that, it's all just, you know, sort of just keep going, right? Working stuff out. The algebra stuff, hopefully, shouldn't be all that bad. You got the I squared being -1 thing going on here. This part, though, that's the part that you want to, you know, make sure that you kind of practice or think about that. And again, remember like what's supposed to happen. So if you multiply by 2 plus I, which is a thing that I've seen people do many times, then what happens next is that the imaginary stuff in the denominator doesn't go away, right? You still have an I term in the denominator. Kind of the whole goal was to get that out of the way. Yeah. Yeah. Okay, so what we need to do with these is first deal with the negative inside the radical. So a negative inside a square root means that that thing is imaginary. So I can factor an I out like that of both of these. And then we're multiplying. The reason that we want to factor the I out first is that if you just multiply, especially the, sorry. Jeez. Looking at what's happening here, there's a negative square root here, negative square root here. If you multiply inside those roots, the negatives are going to cancel, and you lose track of the fact that there were imaginary things to begin with. So that's why we factor the I out first. Now I'm just going to multiply. First, I'm going to continue choking. Okay. Three four is -12. Ionize I squared. Square root of 5 times 12 is the square root of 60. I get you could have left that as just 5 times 12. We're going to end up reducing that thing down anyway, right? So 60 is 5 times 12. And 12 is 3 times 4. And 4 is 2 times 2. So this is -12 times -1 times the square root of 60 reduces down to 2 times the square root of 15. So all told, this is negatives cancel, 12 times 2, 24, root 15. All we're doing all through there is just multiplying. But there's some imaginary number stuff going on, and then there's simplifying a square root, right? And both of those are, you know, useful skills to have. Not something like exactly like that, but I mean, the kind of pieces that are in there, like you need to make sure that you're okay with the fact that I is the square root of -1. Doing this kind of stuff, you know, you might see that somewhere, like simplifying that square root down. And then the rest of it's just multiplication. So, I mean, there's not a problem, you know, exactly like that, but like the individual kind of skills that are going on. So, yeah, it should hopefully be things that you feel comfortable with. Yeah. There are a lot of things in 30. Do you do what? Just whatever the hardest thing is there, just do that. Shoot, I don't know, y'all. Let's do E. Okay. I would like to, yes. We're trying to solve, right? So at some point, I'm going to have to get that out of the square root. It is, for the moment, inside a square root, though. How are we going to get the square root to go away or get it out? Square, right? Like do the opposite. Square that to get the square root, to get out of there. For that to work, it needs to be all by itself on one side of the equation, because if you square, you're squaring like the whole left-hand side, the whole right-hand side, right? Not just like selectively. Here, that's already done. If it wasn't, like if you look at F or G right next to those, then you would start by moving stuff around to get the square root alone, right? Isolate the root first. Okay, so that's already done here. That's good. That means I can jump right into getting rid of the square root by squaring. If I square the left-hand side, I'm squaring a square root. Those are, opposite or inverse operations in a sense, so they, effectively cancel out. That means I need to square both sides though. And when you do that, make sure that you're squaring both sides, right? You're treating x minus 3 like it's one thing and you're squaring it, which means take x minus 3 and multiply it by itself. Which means it's x squared minus 6x plus 9. Okay, so now we're trying to solve, the stuff off to the side, that's not scratch work. Now we're trying to solve this. So what do we need to do? Get everything to one side. X squared negative 6x minus x, so minus 7x. 9 minus 3 plus 6 equals 0. So we've turned this from this equation that had a square root in it that we had to get rid of. We did that by squaring, but now we've turned it into a quadratic, right? So basically, if you want to think kind of graphically about what's going on with the functions, a square root looks like this. It's like half of a sideways parabola. When we square everything, we basically sort of like flip that back up because we've done the inverse. We flip that back up, but we've also, by turning it into a quadratic, sort of like brought in the other half that was kind of missing or wasn't there. Now we got to solve this quadratic. Is it multiply to 6 and add to negative 7? 1 and 6 both negative. Or use the quadratic formula if you want. So I've got 1 and 6 as sort of like possible solutions, but anytime the original thing has something in it that has domain restrictions or is not defined everywhere or has some kind of like, half of everything sort of range, that kind of stuff, we need to make sure that whatever we did to solve didn't, lose track of some of that information, right? So the times that we really, really want to make sure that we go back and check solutions. would be when the original problem has a square root. Or the same thing would be true for any kind of even root, but I'm not going to give you an 8th root or something on a final. A square root, logarithms, and rational stuff. So this is terrible. That I like how much confidence you have. You leaned out of the way. It's like 10 feet from the trash can. Thank you. I mean, I did miss it, but. Those are the times that we want to really, really make sure. I mean, obviously, like you can always check, but those are the times that you really need to. Because if you start with a square root and you end up squaring, or you start with a logarithm, and especially if you like start with a log where you got to do a bunch of stuff, like combine them and change it to multiplication, or any of that kind of stuff, or a thing where you got x in the denominator, those are the times when you lose track of stuff like domain restrictions. Anyway, here, if I go back to the original problem and try to plug in x equals 1, we get the square root of 4 on the left, but on the right, we get 1 minus 3, which is -2, right? Is the square root of 4 -2? No. On the other hand, if I plug in x equals 6, we get the square root of 9. We get 6 minus 3, which is 3. That's fine. So x equals 6 is our only actual solution here. The other one's like a false positive or extraneous solution. For something like a square root like this, where you square both sides and end up solving a quadratic, if you end up with two things, it's basically always going to happen that one of them actually works and the other doesn't, because specifically for a square root, you're taking a square root and it's like you're sort of in a sense, without really realizing it, sort of restoring the like bottom half that's not really there. Right, because the square root, so the square root as like an operation, as a function, as a thing that you do, the button on your calculator, whatever, that means the principal root, the positive one. The times that a plus or minus shows up is when you're going the other way and solving something like x squared equals 4, right? The thing that you're looking for gets squared. Well, 2 squared is 4, and -2 squared is also 4. That's why when we decide to do a square root somewhere, because I want to get rid of a square, that's when you end up with the plus or minus thing happening, which is like, a subtle like difference, but it's about the direction that you're going. If you've got the square root already there, it means like we did here, it means the principal root positive one. If you're doing the square root to get rid of the square, then you got to account for the plus or minus thing. Yeah. Okay. Yes. Can I borrow this test? I thought yesterday afternoon I should print a copy of the test and take it with me, but then I didn't. Okay. That is a 3. Okay. Well, where can we start? Say again. So let's go the other way and move the 4 over and divide the 2 over and try to get this part by itself. And then think about what it means and decide what we're going to do and all that kind of stuff, right? But moving the 4 over, moving the 2 over, that's like fairly easy stuff to do that ought to make our lives a little bit easier. Okay, so this thing, whatever it is, it's 9. Okay. So again, just push stuff around, get it away from this thing so that I can think about what this thing actually does. So I'm basically going to now actually like look at this and try to decide what to do, right? So what does that 2/3 power mean? What does that do? It's a square and a cube root. So the top is a, how many of them thing, right? 2 of them. So 2 copies, so square. The bottom is a, what kind of thing, or break it into pieces kind of thing. Break it into 3 pieces. Well, like as an exponent or as a power, that means a root. So it's a cube root. And a square. You can do it either as the cube root of the whole thing squared, or the cube root, or sorry, I guess I just need to pause somewhere. The cube root of the whole thing squared, or the cube root of the whole thing squared, right? Like either way works because it's multiplication. Trying to solve for this. First, we need to get some of this stuff out of the way though, right? So where should we go from here? Yeah. So don't worry about this. Worry about the big square. That's the way I've got this written. That's the biggest thing that's happening on the left. So get rid of it. Do the opposite, which would be a square root. The square root is going to cancel the square. And now, because we're doing a square root, because I decided to do the square root, plus or minus, right? Yeah. So plus or minus 3. No. So just like in other places, because that cube root is a power, right? It's an exponent. Exponents never really play nicely or like distribute or break up over addition and subtraction. So you can't split that into 2 pieces. First, we need to get rid of the radical, like get rid of that power. So there's a cube root there. Get rid of it by doing the opposite, which would be raise both sides to the 3rd. Yeah, cube both sides. X plus 5. On the right, we've got 3 cubed and negative 3 cubed, which would be plus or minus 27, which is 27 or minus 27, right? So when we subtract 5, you're going to get 22, negative 32. And, again, like, of course, you could check if you want. I don't necessarily have to here because the thing I started with was a cube root. Cube roots are a little bit nicer and easier to work with than square roots are, right? So if that had been a square root in the first place, then I would want to be a little more careful and make sure that I didn't get like a false positive somewhere as a solution, because square roots aren't defined everywhere. Cube roots are. Yeah. Yep. Macy, is that all right? Yeah. 25i, okay. Again, solving. Okay. Get everything to one side. Yeah. Basically, solving stuff, you kind of have a decision to make first, right? So look at like the last couple that we did. Here you started with a square root. I would call that square root of x plus 3. I would call that the messy part, right? So what we did is get the messy part by itself and then get rid of it, right? Undo it, work to do the opposite stuff to clean things up. Here, x plus 5 raised to the 2/3. Well, that's definitely the messy part. We got the messy part by itself, then we work to undo it and get rid of it. Here, there's not really a messy part. There's a whole bunch of terms with x in them, right? So get them all to one side, right? Get them all together, like collect them up, and then see what we can do. There aren't a lot of, hard and fast, like always do this type things that we can really talk about from middle class or math in general, but pretty much all the solving stuff falls into like one of those two things. Like, is there something that's a lot messier than everything else? Okay, get it by itself and then get rid of it. Or is there kind of a bunch of stuff? Okay, well, gather them all up then and then work with it. All right, so we've got them all on one side. Now what? Factor, yeah. How are you going to factor it? Yeah. There's nothing common to all four of them. There are four of them. So you can pair them up and factor by grouping. So look at those two. What do they have in common? X squared. If you take x squared out, what's left? X plus 2. Okay, what do those have in common? 7 and a negative. For grouping to work, we want the stuff that's left behind to be the same. So I'm going to take -7 because that leaves x plus 2. Those match, and that's good because that's kind of the whole thing that factoring by grouping hinges on, but those are identical, which means I can take x plus 2 out as a common factor. And what's left behind is x squared minus 7. Now we have it factored, right? It's like almost by accident kind of, but because you can pair the terms up, we can factor by grouping. These have that in common. These have that in common. You take that out and, oh, look, right? X plus 2, common to both of these, two, kind of the first half and the second half terms, right? We'll then take it out and that's what it leaves behind and like, ta-da, it's factored. Since it's factored, the zero product property says that we can split these up, and that's why we had to move everything to one side in the first place, right? If that wasn't 0 on the right-hand side of the equation, I wouldn't be able to split these up. X is -2, or x squared is 7, which means that x is, Nyla, here's your cue again, plus or minus the square root of 7. thing was degree 3 to begin with, so getting 1, 2, 3 solutions like tracks, right? It doesn't mean it has to have 3, but that's kind of what we might go in expecting. Mhm. Is this so? Turn you guys over. Yeah. So really, that's 3 things, right? -2, positive root 7, negative root 7. I'm cool with you just writing that as plus or minus. So it's not quadratic, it's cubic. So quadratic formula wouldn't work. Pretty much something like that, you would, right, yeah. Grouping, or it would be like find a 0, do division, then solve that. You're not going to need to do that on the final. Yeah. Okay. Somebody asked me something and I don't remember what it was now. 32. Okay. Do you care which one? Yep. Okay. We are trying to find the domain, right? If something asks you to find the domain, what I want you to try to think through is first deciding what kind of thing is it and what does that mean about the domain. So what kind of thing is this? What's the thing, looking at this function, what's the thing that stands out the most to you? The square root, right? The square root's the biggest thing. I mean, both literally and like kind of most important in terms of what's going on, right? So it's the square root. Add some little flair to that. It's a square root. Okay. For a square root function, what do we need to worry about to find the domain? And finding domain, like you can often think of that in terms of bad stuff. Like what bad stuff could happen for a square root? What would be bad? What would be a problem? Negative underneath, right? If the stuff underneath is negative, then the square root is not a real number, which means the function is not defined. Because functions are always real numbers to real numbers for us, right? So if the stuff underneath is not positive or 0, like 0 or bigger, right? Then the function is not going to be defined. So we need to make sure the stuff underneath, the radicand, is, you want me to say not negative, or you want me to say 0 or bigger? Okay. Is greater or equal to 0. This list I made before about checking solutions, this list is pretty much the same list as stuff that gives you domain issues. Square roots, you can't have a negative underneath. So you got to make sure that the stuff underneath is greater than or equal to 0. Logarithms, you can't take the log of a negative number, you can't take the log of 0. So you got to make sure the stuff inside is positive. Rational functions, something that has x in the denominator somewhere, you can't divide by 0, right? So you got to make sure the stuff in the denominator is not 0. That's pretty much those 3 kind of like families of functions. That's really all we've talked about this semester, where there are like domain issues that happen because of stuff that's not defined. All right, so the way I would do this is take this and figure out where it's greater than or equal to 0. Or if you want, you could just set it equal to 0. And then we'll have to, sort of do some work on the back end to figure it out. But let's add 6 to both sides. and multiply by -3. And divide by 2. And then I'm gonna figure out the inequality, or, figure out which side of this thing I want by just testing points. Again, if you want to just solve this as an inequality all the way down, that's fine too. If I take -12 and go back here, that's -4. -6 minus 2/3 times -12. So that's -6 plus 8, which is 2, which is positive. On the other hand, if I try to plug 0 in, I get -6, which is negative. This side is okay then. This one is not. So the domain for this function is what? -infinity to -9 with a bracket. Because at -9, you get 0 underneath. The square root of 0 is 0. Okay. Mostly okay. Kind of okay. Everybody's still writing. Okay, Macy nodded anyway. Anyway, anybody have any issues with that? Okay, cool. All right, go ahead.
So you want them to do positive, not
Yeah, because this is, so I'm plugging into the stuff underneath, right? So here I would have the square root of -12, or sorry, the square root of 2. Square root of 2 is fine, right? That's a real number. I'm happy with that. Here, if I try to plug 0 in, I would get the square root of -6. That's not a real number. That means the function is not defined there. You can all, you can do that part by looking at a graph too, right? Like if I looked at the graph of this thing, I'm gonna see that thing sort of going that way, right? So it exists left of -9. It does not exist to the right of -9. I would want to see, you at least work through like this part or something to figure out where that value is, right? But you could use a graph to help you make that decision about sort of which side of it to take.
Is the compound interest stuff going to be?
Let's talk about it. So again, you'll have the formulas. So I'm going to give you those. Let's look at 49 on the review. You invest $10,000 at 3.25% compounded continuously. How long will it take to grow to $15,000? We're going to use the second formula. How do you know you're going to use the second formula? Because it's compounded continuously. Okay. And how would we set it up?
is 0.03.2
Yep,
and then you don't know the time.
right. The question was how long? So we don't know T, right? So T is the thing that we're looking for. You're investing, you're starting with $10,000. That's your initial investment. That's the principal. You want to know how long it will take, so find T, to grow to 15,000. So I want to know how long, what T value can turn this into 15,000 at 3.25%. So 0.0325, slide the decimal 2 places or divide by 100. Everybody okay with the setup? Okay. Now, how do we solve that? Divide by 10,000. This is we're solving, right? So this is here's the messy part. Get the messy part by itself, right? Moving the 10,000 over, that's an easy, that's a cheap thing I can do to work on getting the messy part by itself, right? We always want to look for, low hanging fruit. Do the cheap stuff first. Yeah. Yeah, so that's 15 divided by 10 or 3 divided by 2 or 1.5 or like whatever, right? I'm going to end up just punching all that into a calculator at some point. So, don't worry about like trying to simplify or reduce the fraction. If it was a decimal that gets like messy when you do 15,000 divided by 10,000, just keep that whole thing, store it in your calculator, type it in again, use the answer thing, whatever. Just don't round too much in the middle. Don't round it all in the middle of the problem. That's how you end up crashing probes into Mars and stuff. That might be an outdated reference now. So that, right? Now what? Take a natural log because it's E, right? It's E. You're looking for a thing that's in the exponents to take a natural log. Okay, what would this look like if we rewrite that as a natural log? Well, it's a natural log, so the base is E, right? If that's what you're talking about. You're talking about like the subscript?
I thought we were changing
So give me an exponential and a log with say like 2. 2 to the third is 8. So the log with base 2 of what is what? Log base 2 of 8 is 3. Because this thing and this thing and this thing and this thing need to like switch places, right? So here things look a little, scarier, but natural log, so it's a log base E, right? Of, go ahead, Bridget. 1.5 is 0.0325 T. Does everybody see this the same thing? You're doing the same thing there, right? Even if you're just thinking of it as like following a pattern. This thing that was kind of in the inside of the exponential, right? It's kind of stuck in that exponent where I can't get to it yet. Well, doing the log should be the thing that gets it out, right? So it wouldn't make any sense really for this to be the thing that moves into the log because, well, that's no more good to me there than it was, here. So this and this need to kind of swap roles in terms of like what's inside and what's outside. And now we're just dealing with solving for T. So T is whatever the log of 1.5 divided by 0.0325 is. Give me a decimal place or something. $12.5 years. Good, not so bad? Okay, good.
Do we need to solve it, like, or is that the?
Yeah, no, we did solve it. Yeah, the question was, how long will it take? We found a time. Well, I mean, if you plug it back in, it should check out.
Yeah.
Right? Now, since you probably rounded at the end, it would, make it not land right, bang on the nose. Right, yeah. Yeah, so you could do that, but the question was how long, so the answer should be. Yeah. Okay? Do you have anything else real quick? Okay, cool. Well, you guys that, test Thursday especially, but, let me know if there's anything you need help with between now and then. I mean, this applies to everybody too, but I know it's, a little more urgent for some of us than for others. So I hope everything goes well with other